So a lot of the key considerations that we look at for site availability purposes it's a multifaceted problem. One, we're looking at areas that are in close proximity to the South Pole to meet the science needs of the community. We're looking at aspects with the slope for the vehicle to land on, as well as slopes of nearby terrain that is safe for the crew to reach points of scientific interest near different potential landing sites. We're also looking at areas that have a constant view to the Earth to support the communication needs of the vehicle. Uh, not only during descent and ascent, but across the surface, and very important during the surface EVAs, so we can have good, strong communication links to support the video and data transmission needs back with Earth. Uh, as Tamara mentioned, with solar arrays, we're looking to have continuous sunlight throughout the surface expedition. So this means about 6.5 days that we're going to need that landing site to be constantly illuminated on the vehicle to support power generation. And also, you want the surface sunlit so that you can support the EVAs, so the crew is not relying strictly on uh, lighting provided by the vehicle or lighting provided by the suits. When we're looking at sites, we have to consider the landing accuracy. And so while we identify a target site that is not without error, Artemis 3 is using a 100-meter landing radius for accuracy per the requirements. And so we have to assess the safety of a site not only as a point location, but throughout the entire that landing accuracy around the target sites, and that correlates with how much data is actually available. So what NAC imagery, what digital elevation model data sets are available at different locations plays into considerations for some regions against others or some sites against others. And then we also have to combine all these aspects together in order to look at what the different vehicles bring together. SLS and Orion, won't provide opportunities every potential gateway orbit based surface day. As we saw with Artemis 1, there were very specific launch opportunities. The same would be true for Artemis 2 and Artemis 3. So we're bound by that. We're bound by vehicle-based constraints on course, lighting and comm, as we mentioned before. And the last point is that a region, as we have had these 13 regions announced, is a fairly large amount of surface area. At the smallest regions are 15 by 15 kilometers, and each region does include multiple potential landing sites, and that's what drove those regions to be considered uh, viable and why they were included in the announcement last year. Next slide. So this one is based on landing slope, and so we're trying to show where those 13 regions are with the orange boxes and a polar stereographic projection map perspective. The areas that are shown in green have a slope less than 10 degrees, and then when you start to factor in that slope being less than 10 across the dimensionality of a vehicle size and throughout the entire landing radius, the quantity of green terrain starts to decrease. But this is just as a starting point, on a per pixel basis in the data sets that we have, what is viable less than 10 degrees. So, where the slopes are viable for landing is, an initial screening point. Next slide. For communication, since we will need direct with Earth communication, sites that have better Earth visibility, meaning that the Earth is able to be, more above the lunar horizon than other sites, will be very important. And the 18.6-year average Earth visibility data set is being plotted on the map against the 13 regions, where colors towards red are going towards higher Earth visibility percentages, and colors going down towards purple are going towards lower average Earth visibility data sets. Next slide. This plot shows the 13 regions against illumination, and this was taken as a a single kind of projected kind of rendering of what illumination could be. You'll see some areas are much more highly illuminated than others, and you can kind of derive what a terminator line would look like for areas with and without sunlight, according to this perspective. But as we said, we need to have illumination across the surface day. So with a 6.5 day surface day out of the 28 days, you end up with quadrants of the lunar surface that are able to be remain sunlit over that entire surface day duration. And next slide. This one deals with the landing, so going upon descent. So missions from NRHO or the Gateway orbit, the trajectories that go in towards this particular site do vary orbit to orbit or rev to rev. And so the red lines are showing potential landing trajectories going into the same target site as they would be, for different, gateway orbit revs. And so one could also think of the lighting conditions, associated with those particular trajectories would also vary per rev. And so that's another very important, relevant factor for doing the assessments. The line on the top left had better illumination compared to the line at the bottom left at that starting point. And then, as we're seeing in the video, that illumination is changing, and we're looking at this transition very quickly. This entire video is the 2026 year, but you can see the shadows and how those change time. Eventually, what is found is that in the 25-26 time frame, months of November, December, January, we have the solar elevation angle being highest above the horizon, and months of around June, July tend to be where it is lowest on the horizon, meaning that there is less average sunlight, as you're starting to see where the video is phasing in currently. That means that the Earth summer months in 26 are going to always be more challenging from an illumination perspective. And the winter months in 26, 25, 26 kind of time frame are provide better opportunities. And that does change every, on a yearly basis. We do see that shift in optimal illumination move about 2 to 3 weeks forward in time, or per year. I think that is all of my slides. Tamara, I think it's back to you now.
I think that's all we had for this pitch, but Sam, are we going to have a Q&A part?
Yeah, that's right. We kind of combined those two talks into one. So now we have a few minutes here for questions. Take the next few minutes to answer any questions. So I see some questions in the chat here. I see a question. Some of the questions have been answered. There's a question here from Dean Epler about, have we established flight rules for landing safety that can be applied to 3 sigma landing ellipses, including how much of the ellipse is in the dark and what's the biggest patch of shadow that we can accept before a candidate landing site fails for safety reasons?
I would say that the goal is to get there. The iterative process, we're looking at the vehicle's design, and as Bryan was showing, the various things and the considerations, and those will eventually roll into landing safety assessments and flight rules. So we have a little ways to go yet with our operations team and working through the design and such that will drive what the flight rules end up being. Let's see, what else? I see the direct to Earth visibility. Bryan, would you like to answer that one?
I believe that yes, we are saying direct with Earth visibility is going to be required for Artemis 3 because we will not have Gateway will not be present by that point in time. So we will need to have the communication back with Earth. And the Earth ground stations that would be used would be those that would be part of the SpaceX communication architecture.
See a question here from, let's see, well, is the trajectory shown implying that good lighting is needed to about 88 degrees south of going to remove Shackleton?
It was meant as a zoomed in version. Lighting will be based on the needs and assessments of the TRN capabilities of the vehicle. That is all dependent on their incoming trajectory and when they start the actual use of their TRN system. The purpose of that plot was focused on trying to illustrate the differences in approach direction, let alone not the distance of which TRN would be used.
I see a question on, is the lander expected to provide any active illumination during the final stages? That is not a requirement that NASA levied on the lander. I know our crew office and operations office is currently working with HLS and our SpaceX friends on the crew's role in landing the vehicle. So that is ongoing work. Also ongoing work is the backup sites. So the goal with the end-to-end mission availability, when we launch off the pad, there is a final site, of course, selected, and everything is in the system to go to that site. The part of the iterative process of the site selection is also working with all of our teammates and stakeholders on what those contingency scenarios are going to be. So at this time, we don't have a list of backup sites to a prime site number. So we look forward to continuing to work through that with all the stakeholders. But right now, during a launch, where the goal is going to that site, the prime. Bryan, I think there's a good one for you being asked. Do you know if the good Earth visibility periods coincide with
Yeah,
summer?
I
Okay.
see that. Yeah, I see that question. So yes, we are seeing those trends in the analysis. There are certain portions of time when those line up very nicely. There are other portions of time where they don't line up, so we're trying to find ideal. You're finding many more sites being available in the times when they do line up, and then it's a question of if SLS and Orion is able to launch from Earth to reach the gateway orbit on that same particular rev. And that's how we get to portions of the mission availability story.
Another good one for you, Bryan, is the lighting constraints versus the direct to Earth visibility. Is one more important than the other?
Both are equally needed to satisfy the constraints. So we're not going to sacrifice one for the other. Both are necessary.
So crater-free area. There is actually a document out there already public that kind of identifies some of the crater population requirements. So anybody can go look at it. It's called the Disney. So if you're curious about some of what our vehicles and other things need to design to that document is out there for folks to read.
I think it's important to remember the Disney is not a requirements document. It's a environments guide document.
Yes, thank you for that clarification.
I might take a moment just to answer Jack's question about landing simulators for a moment here. JSC and Langley are working together to develop simulators and trainers at Langley, and of course working with SpaceX as well to get high fidelity simulators into the preparation process.
Thank you, Noah.